Okay, good morning, everyone. Let's get started. Hopefully you have finished up and submitted milestone 2, and you're working on your third weekly deliverable for your final project. I don't have anything to share. Any questions, comments? So far, so good. Just a reminder, if you course correct, just let us know what change you've made to your weekly milestone. And from what I can see, you're all making good progress. Okay. All right, back to course material. We're working our way through open problems in the field, which we are almost done with. We're working our way through arguably the biggest challenge in the field at the moment, which is evolving or training machines in silico and then trying to transfer them to reality and somehow cross the reality gap. In lecture 14, we looked at the first approach to this, which is to sprinkle noise on the simulator, make sure evolution doesn't exploit abstractions or inaccuracies in the simulator. We finished talking about the Golem project last time, which was to bring in another new technology, 3D printers, and automatically evolve both bodies and brains in simulation and try and automate the manufacture of those evolved machines and try and cross the reality gap by just crossing the gap as many times as you can with different robots, with different bodies and brains, and hope for the best. Hope for that some of them will cross the gap. We made our way partway through lecture 16 last time. This was my contribution to this problem, which became retroactively known as the Resilient Machines Project, which is trying to evolve a simulator that reflects the reality of the physical machine. So basically trying to narrow the gap by quote unquote bringing the simulator closer and closer to reality. Tricky to do by hand. Maybe we can evolve simulators to do so. So that was lecture 16. I showed you, we were starting to look at last time how this works, how this physical machine goes about evolving simulations of self. I will finish showing you today how at the end of this process, it has an evolved simulator that it uses to evolve controllers to walk in reality. And I'll finish today, lecture 16 today by talking about phase 2 of this project. If we have a physical machine that can evolve simulations of self, then when self changes, it can re-evolve the simulator to explain its changed situation, and then use the new simulator, the new evolved simulator, to just keep evolving controllers for what we ultimately want this machine to do, which, as usual in this course, is move from left to right. Yeah? Okay, so very quickly, I was walking you through a typical experiment last time. The robot starts with very little knowledge, performs a random action, gets one sensor motor pair, starts evolving simulators to explain that single sensor motor pair, that one piece of real world experience that it has, comes up with lots of different simulators that can all explain that one little bit of real experience. So we go back, the physical robot goes back and forth between real and sim. This is the 8th action. And this is the 8th return to sim. Each of the sims that you see here is trying to explain all 8 sensor motor pairs that the robot has experienced at this time. And I'm showing you the 8th pass through because during this 8th pass through, just for whatever reason in this particular experiment, the robot had an aha moment. You'll see at the beginning of this animation, it has a pretty inaccurate explanation of self. There's a whole bunch of different simulators that explain the previous 7, but none that are explaining the previous 7 plus the 8th experience. But suddenly the evolutionary algorithm, by mutating and copying some of these simulators, stumbles upon this one, then this one. Now it's armed with this simulator, and by the time it gets to the 16th action and the 16th attempt to evolve simulations of self, this is what all the evolved simulators look at this point in time. All of the conceptions of itself have narrowed in on this explanation, and every new experience that the real world robot gets, these simulators seem to explain it. So from the robot's perspective, it's done. As far as it knows, it understands itself. We ended last time by making the observation, the observation was made actually from one of you, that the robot is not performing random actions. Random actions are good, but you can do something better than random actions. If you have a whole bunch of ideas about self, you can use those self models. So I'm going to talk about these evolved simulators and self models now as one and the same thing. If you have a bunch of different self models, before you perform a real action in reality, you can ask the self models what they think is going to happen. You take that action, you send that action to all of these little simulated versions of yourself, and all these little simulated things move. They perform that action, and they make a prediction. Each of them makes a prediction. The prediction is sensory prediction. In essence, each self-model says, I think if you rotate motor 3 and 4 like this, I predict that you're going to tilt like this. Another self-model, which might be a little bit different, says, no. If you perform that action, if you rotate motors 3 and 4 in this way, I predict something different. I predict you're going to rotate this way and then this way. Yeah? So these self-models can agree or disagree in their predictions about the sensory repercussion of an action. So far, so good? Okay. So in the Resilient Machines project, there are actually 3 separate evolutionary algorithms that are running. I've shown you one of the 3 so far. The first evolutionary algorithm is evolving populations of self-models, or populations of evolved simulators. The second evolutionary algorithm is responsible for coming up with the next action that the physical robot performs. That second evolutionary algorithm is not evolving populations of simulations, it's evolving populations of controllers, not unlike what you've been doing in the assignments. But the fitness of those controllers is not how far it makes the simulated robot move, it's how much that little controller makes the self-models disagree. Can take a moment to kind of wrap your mind around that. Make sense? So when we go back and forth, or when the real robot goes back and forth between sim and real, it's running these 2 evolutionary algorithms continuously. One is trying to evolve accurate models of self, and the other one is trying to evolve new actions for the physical robot to perform that will give the physical robot new information about itself. If the second evolutionary algorithm finds a controller that causes the self-models to disagree, and the physical robot carries out that action, whatever the sensory repercussion is, the self-models, at least one of them is going to be wrong. Since they all disagreed, somebody's got to be wrong, and it's possible that they're all wrong. What happens at that point when the physical robot actually carries out one of these self-model disagreeing actions? The real robot gets that new sensory result and then goes back to simulation. We unpause the first evolutionary algorithm and it continues to evolve self-models. What happens at exactly that moment when the first evolutionary algorithm starts up again? The physical robot has just carried out an action that the self-models were disagreeing about.
I would guess that it takes the self-model with the highest fitness, which is the closest to the reality, and then mutates it and evolves.
Absolutely, right? So assuming one of the self-models was correct or close to being correct, the fitness of that self-model doesn't change very much, right? It's kind of explaining, or retroactively it has explained that action. What happens to the fitness of all the other self-models in the population? The ones that disagreed and got it wrong. Their predictions were wrong. What happens to their fitness?
It would be bad.
It would be bad. The fitness, suddenly if we recalculate the fitness of all of those self-models, those fitnesses go down, and they're probably killed and replaced by randomly modified offspring of the one that made a good prediction. Everybody see that? So we've got these two evolutionary algorithms that are kind of in opposition to one another. They're playing off against one another. If you remember earlier in the course when we talked about evolutionary algorithms, we talked about fitness landscapes, this abstract a mathematical construct that we can use to think about evolutionary dynamics, how evolving populations operate. When we talked about fitness landscapes, we thought about different points in this space, each point representing a different solution to our given problem. Now we're talking about populations of different self-models, and we might have at a given point in time a whole bunch of different self-models that all have relatively high fitness. They're all explaining the experiences collected by the physical robot pretty well so far. The moment we get a new experience from the physical robot about which these self-models disagreed, it's not necessarily that the points move. We haven't changed the self-models. It's that their fitnesses have changed. So in effect, these new experiences coming back from the physical robot alter the fitness landscape itself. So these points, these self-models, are now not climbing the slopes of hills, they're climbing the slopes of waves. The actual surface itself is changing, and by having this robot seek actions that cause them to disagree, the physical robot is actively trying to disprove its hypotheses about itself. In an essence, in a way, the robot is acting like a scientist. It's trying to disprove its own hypotheses with new experiments, where an experiment is an action that it performs. And by doing so, it rapidly converges on a good explanation of itself. This particular self-model is hard to disprove. Towards the end of the experiment here, the second evolutionary algorithm that is evolving actions to cause the self-models to disagree, it starts failing. It can no longer find new actions that when it supplies those prospective actions, those actions it's thinking about performing, when it sends them to the self-models, they all agree. All the self-models say, we know exactly what's going to happen. And as you can imagine, if the physical robot does carry out those actions, they were all correct. There is no action the robot can find that will depress this slope in the fitness ocean now. It's solidified into a fitness landscape. Make sense? Okay. I started this particular tangent of discussion last time, and when I did, I started by mentioning a concept from developmental psychology called motor babbling. Remember that developmental psychology is the study of human development, or the study of how little kiddos grow up into adults. If you've ever spent any time around a little kid, they will rapidly destroy all furniture and toys and food and anything else you put near them. Little kids tend not to sit quietly for very long. Developmental psychologists often explain what they're doing as motor babbling. They're just kind of randomly doing as much stuff as they can to learn about their own bodies. It's that explanation in retrospect after the Resilient Machines project is half right. They are doing things to learn things about their body, but they're probably not, we still don't know, they're probably not motor babbling at random. They're not performing random actions. It's possible that all of us, when we were little kids, we were actually running an algorithm that was choosing for us which action to perform next. Possibly, that algorithm looks something like the algorithm that I just described. Like I said, we don't know, but there is mounting evidence to suggest that's the case. In your cerebellum, at the very back and bottom of your brain, in the cerebellum, there is now known to be what are called forward models. These are little bits of your cerebellum that seem to be dreaming up little actions. They connect to the motor strip. We also talked about the motor strip in your brain. It's that part of your brain that would be covered if you're wearing earphones. The forward model seems to dream up or collect actions from motor strip, things you might possibly perform in the future. Then there are little different parts of your cerebellum that light up that seem to correlate with sensory repercussion. So if you actually perform an action and you feel in the real world a sensory repercussion, your brain lights up in terms of that sensation. So there's another part of your brain called the sensor strip where it lights up when you feel things. Bits of the cerebellum seem to say, they connect to motor strip to say, if you do this action, I predict you're going to feel this sensory repercussion. There's growing evidence for these things in you that can make predictions. If you have these in the cerebellum, maybe you have several of them, and maybe you use them when you're a little kiddo or when you're learning to play a new musical instrument or learn a new sport or learn a new branch of mathematics. Perhaps you're using them to decide what to do or to try next. All unknown, all hypothetical at the moment. I've mentioned several times in this course, there's a lot of big open questions in robotics and neuroscience remaining to be answered. Maybe some of you will help find an answer to these questions someday. Okay. All right, so I've mentioned 2 evolutionary algorithms so far. One evolving self-models, one evolving what the physical robot should do next. At some point, these 2 evolutionary algorithms run out of gas because the robot converges on an explanation of self. This simulation was not written by hand by me. It was evolved by the physical robot. Okay, now the 3rd evolutionary algorithm comes online, and this evolutionary algorithm is more or less the same as your parallel hill climber. It's searching over the space of sets of synaptic weights. And the fitness of each of those sets of synaptic weights is how well it gets the evolved simulated robot to move from left to right. This part, at least, should look pretty familiar to you. Okay, Resilient Machines Project contains 3 evolutionary algorithms. We run this 3rd evolutionary algorithm, and in this particular experiment, this is what this 3rd evolutionary algorithm came up with. This was the result of the most fit set of synaptic weights. The set of synaptic weights is the genotype. This is the phenotype. We took that set of synaptic weights, downloaded it onto the equivalent of a Raspberry Pi in 2006, and this was the result. How do we do? Not bad. There's obviously a very long blooper reel of all the things that didn't work. This is one, at least, that did work. I worked on this for 2.5 years. It took us a long time to debug these 3 evolutionary algorithms, get them to work together. It took a lot of time to subjugate all of the variables and constants that are in physics engines, putting them under the evolutionary control. It took a long time to get all this to work. We shot this video about 3 in the morning in a basement lab at Cornell. It was myself and 2 other investigators on this project, and we went absolutely crazy. It took forever to get to this point. There was an undergrad sitting at another bench working on a completely different project, didn't know anything about this, turns around 3 in the morning, sees this thing crawling along the desk and says, dude, that's the evil starfish. So, for better or for worse, the formal name of this project is the Resilient Machines Project, but for most roboticists, it's now known as the Evil Starfish Project, for better or for worse. There you go. Okay. All right. That's the end of phase 1. Not to worry, phase 2 will go a lot faster. Okay. When we're dealing with physical machines, we've said this many times at this point, machines and organisms never enter the same river twice. The world around us is always changing, and we are also changing, as do machines. We grow up, and some of us also start to wear out eventually. In this case, we sent one of the grad students working on this project, we sent them into the cage here with the evil starfish, with a screwdriver, and they manually loosened and removed the lower leg. You can see there's nothing left of the right lower leg except the little stepper motor here, the knee motor, and the lower leg is gone completely. Every once in a while, the physical robot stops from trying to move from left to right, and it replays some of these 16 actions that it performed during motor babbling, during the earlier phases of the project. Here's the evil starfish replaying one of those 16 actions. And before, when this robot did this action before, it used to tilt 40 degrees to the left, but now it's only tilting 20 degrees to the left. So from the perspective of the physical robot, it says, wait, I have to stop moving from left to right because something has changed. This action has now produced 2 different sensory repercussions. Before, it was 40 degrees, the repercussion was 40 degrees to the left, and now it's only 20 degrees to the left. Something has changed. From the robot's perspective, what can it conclude has happened? Self has changed. So if I were to blindfold you, if I were to knock out all of your sensors except your inner ear, you could still feel vestibular information. I picked you up and took you somewhere else and put you down, and you did something that produces a sensory repercussion you're not used to. You might conclude something has happened to you. That's one option. What else? What else might have happened? I'm sorry to break it to you, it's not all about you.
The environment.
The environment might have changed. Self might have changed, or non-self might have changed. It turns out there's an infinite number of explanations for what might have changed. The robot's mission is still to move from left to right along the table. What's a poor robot to do at this point? What would you do? Something has changed. So let's start up the first evolutionary algorithm again and search over the space of self models. And you're right, actually, in this first paper, we restricted the robot's hypothesis space to self. We said, yeah, we've changed something and we've changed you. We haven't told you what about you has changed. And it turns out there's an infinite number of possible things that might have changed. Here's the robot, here's the first evolutionary algorithm running, and here is its thought process, so to speak. You're watching a series of increasingly fit self-models that explain the original 16 actions minus the action that has a changed repercussion. So it's taken that new experience and replaced the old experience that it can no longer replicate. So this particular these self-models have to explain 16 experiences. The old 15 experiences plus the new one. You'll notice the result of some of the mutations here. At some point, the robot thinks that its leg has shrunk. Doesn't hold up very long in the evolutionary algorithm. It explains some situations but not others, and it eventually relatively quickly hits on the right explanation, which is that its right lower leg is missing. It's not a perfect explanation, though. Why not? Might be difficult to see from back there.
There's like a tiny little piece of the lower leg.
So if you were able to ask this robot, if you hooked it up these days to a large language model, it'd say, I think my right lower leg has shrunk to about 1 millimeter in length. Why would we build in mutation operators that can increase or decrease the size of parts? That seems ridiculous. We can shrink and grow in size. Traditional robots, not so much.
Like, if a part of it broke and you need to replace it with another and it wasn't the exact same, it's supposed to be resilient, so.
It's supposed to be resilient. Maybe it wears out and we replace it with a new part, but we couldn't order that old part on Amazon, so we had to get a slightly different part, which was a slightly different geometry. Absolutely. This project was funded by NASA originally. NASA was interested in evolutionary robotics as what they call methods of last resort. So for very good reason, NASA is an extremely conservative engineering firm. They build redundancies into redundancies into redundancies, because if they send a rover to Mars, as far as we know, there's nobody there to fix things if something goes wrong. So NASA also builds in on top of all their levels of redundancy what they call methods of last resort, which is if the machine seems to really be in trouble, if it's performing actions that are producing sensory repercussions that are far outside its specs, and the robot knows it, then and only then is the rover allowed complete autonomy, meaning it's allowed to try stuff up, dream up new ideas, because the alternative is a several $billion in taxpayer dead rover on the surface of the red planet. So, from NASA's perspective, we built in mutation operators that can increase and shrink components, not necessarily because of replacement parts, although that's one possible explanation. It's possible that part of the leg might rip off, some of the metal might get sheared off. There are lots of things that can happen in space or during descent or on the surface of a partly understood planet where the geometry of the robot can change in unexpected ways that are hard to anticipate. So we allowed the evolutionary algorithm more freedom to play with the mass distribution and the geometry of the robot. You might notice watching this that some of the parts also get bigger in size sometimes. Why do we put that in? Getting smaller makes sense. Parts get sheared off, broken off, springs break. How could a robot or a rover get bigger, so to speak?
I mean, if it got covered in snow, it would like weigh more.
Covered in snow, regolith, all that, you name it, right? If you've ever seen any videos of the Mars rovers, whenever there's a little bit of gunk that gets stuck on the wheels, NASA panics. They'll spend weeks turning the wheel like this to try and shake off the clod of whatever is stuck on the wheel. So completely autonomous planetary rovers can actually unanticipatedly increase and decrease in mass. Okay, kind of an aside. Anyways, we now have a robot that's adapting its self models to track changes in itself that it cannot see directly. Remember that this robot doesn't have a camera. It can't see itself. If it could, if the robot could directly see or sense every possible thing that could go wrong, the problem would be a lot easier. The thing that keeps NASA engineers awake at night, and engineers in general, is when something goes wrong that can only indirectly be sensed by the robot's sensors. Okay, so we now restart up the third evolutionary algorithm, which is evolving populations of sets of synaptic weights. that cause the robot to walk from left to right. At the moment we start up that third evolutionary algorithm, when this third evolutionary algorithm was running before, it had at least one highly fit set of synaptic weights that caused the intact simulated robot to walk from left to right. Tell me about the fitness of that set of synaptic weights now that the robot, quote unquote, knows it only has 3.5 legs. What happens to the fitness of that controller, do you think? We take that set of synaptic weights, or the physical robot takes that set of synaptic weights, downloads it onto its simulated 3.5 leg self. What do you think happens?
Probably does worse.
Does much worse. Fitness goes way down. The fitness of most of the controllers in that third population drop. Evolution continues, keeps evolving controllers on this simulated injured robot. Fitness starts to climb again, and eventually we got this particular set of synaptic weights that causes the robot to move from left to right. In retrospect, maybe not in the way we would have liked it to do so. So perverse instantiation has reared its ugly head again. Why is this perhaps not the way we want a rover to walk along on the surface of Mars, or any surface for that matter? What's up?
Well, before it was like kind of crawling. Now it seems like it's almost like standing all the way up on those legs, which like looks like it could maybe break part of the robot. I don't know.
It's certainly, the self model is being optimistic at this point, right? It's maybe overestimating the strength of the motors. What else is problematic about this particular gate?
Looks like it's heavily reliant on friction along that terminal yellow point.
Yes, it's relying quite a bit on friction in this case. Yeah, you're right in terms of the right leg, back leg. I don't know at this point. Here, let's see this set of synaptic weights transferred from simulation to reality. I see a lot of, okay. Not great. We're crossing the gap to some point. There's still rightward travel. When we showed this to the NASA engineers, they kind of also did the same thing. They would much prefer this to the rover is dead. There's nothing else we can't seem to get the rover to do anything. From NASA's perspective, if there's grievous injury and we have an autonomous process, which in this case are these 3 evolutionary algorithms working in concert, a little bit of recovered functionality is better than no functionality at all. So, okay, what else? But what else is wrong with this? It's okay, I've got thick skin. Go ahead.
Well, if it's collecting data, then how is it going to do that? Like, where is the sensor? It's going to be all over the place. If it's like video footage, it's going to be of the sky and then back on the ground and around.
Absolutely, right? The NASA engineers aren't so happy about the main body exhibiting a lot of 3D rotation and acceleration for lots of reasons, right? You'd like it to stay relatively steady. This robot's kind of throwing itself all over the place. It's also walking in a semicircle. Some of you might have actually got this solution with some of your quadrupeds in A10. Here's perverse instantiation at its best. The robot says, all you did was tell me to walk from left to right. I'm doing exactly that. I happen to be facing in the opposite direction when I finish my gait, but you didn't say anything about maintaining orientation. If we kept running this controller on the robot, it'll just walk in circles. So in the long run, not really what we wanted the robot to do, but not bad. Okay. Any questions or comments about the Resilient Machines project? No? Okay. All right, we're going to stop the lecture here just in the interest of time. And we're going to move on now to lecture 17. So we've seen 3 attempts to cross the reality gap so far. Add a little bit of noise, throw as many robots across the gap as you can, and evolve simulators to narrow the sim to real gap. We're going to look at another approach that came after my work, which is known as transferability. And so let's first start by looking at the why of this project. What was the rationale? The idea behind the transferability project was, could we evolve controllers in simulation against 2 fitness functions? The first fitness function is the usual one. It measures how well or how poorly the robot does at whatever we want it to do when it's armed with that controller. Imagine we can measure a second feature of each controller in the evolving population of controllers, which is how transferable it is. We saw in the Golem project that some robots transfer across the gap better than others. Some of that has to do with the robot's body, but also it has to do with the controller. A controller that causes a robot to exhibit peristaltic motion, this sort of inchworm crawling that we saw when we talked about in the legged locomotion lecture. Peristaltic motion, if a controller causes a robot to do that, that actually transfers pretty well to reality. It's relatively slow motion. We're using a lot of friction to move. A second controller that gets the robot to stand up, like the one we just saw, and sort of prance around, use very high velocity motion, maybe induce a little bit of a flight phase in the robot's motion. Those kinds of controllers, those fancy controllers, tend not to cross the gap very well. Okay, so maybe we can actually measure the transferability of given controllers, and we're going to try and evolve controllers on simulated robots to produce useful function and be transferable. But that idea, that question raises a second question, which is how? How do you define the transferability of a controller? Thoughts? What would be the simplest way, the most obvious way to measure how transferable a controller is?
You could like compare the sensor values of the like simulated action and then the action in real life.
Absolutely. Take every controller, run it on the real robot, and then take the difference between the generated real sensor values and the generated simulated sensor values. The closer the match, the smaller the difference between those sensor values, the more transferable the controller is. Makes sense? Very obvious. It's got an obvious downside. We've got a population of controllers. We evaluate every controller on the simulated robot, and we evaluate each of those controllers on the real robot because we need to compute transferability. We're transferring every controller from simulation to reality. Why do we even need the simulator anymore, right? Now we're just back to evaluating hundreds or thousands or millions of controllers on the real robot. So a good starting point, but that's not going to work. It feels like there's a bit of a catch-22 here. Okay, let's pause for a moment. Well, and let's talk about this. So the general idea we're going to pursue here is we're going to compute 2 floating point values for every controller. How well that controller produces the desired behavior in the simulated robot, and the other that rewards transferability somehow. Or the second value measures transferability somehow. The most obvious way to do it would be between simulated and real behavior. Okay. We're going to just, that's not what we're going to do, but let's stick with that for a moment. Let's imagine we did do that. We've got 2 numbers. We've got 2 fitness values for every controller. How do we combine these 2 numbers in some way to determine in this population of evolving controllers which ones are killed off and which ones survive and produce randomly modified copies of themselves? We need to somehow have a fitness value. We could sum them. Let's assume F1 is the first fitness objective and F2 is the second fitness objective. Some of you might already be doing something like this in your final project. Maybe F1 is how far the robot travels, and maybe F2 is how much time the robot spends off the ground. If you were evolving long jumping, for example, you might compute the horizontal and the vertical displacement of the robot. So you might also have two fitness objectives. The tricky thing in evolutionary algorithms is how to combine them. Has anybody tried running a fitness function that sums two values yet? Yeah? There's a bit of a problem with it. What's the problem with summing? Any tricky aspects yet to summing them?
Sometimes I feel like it goes more towards one fitness than the other one.
Evolution is not an optimizer, it's a satisficer, and she's also kind of lazy. Sometimes she'll say, you know what, one of these fitness objectives tends to have a wider range of values than the other one. Therefore, it's so much easier for me through mutation and reproduction to make one of these values bigger just because the general magnitude of that number is larger. So it kind of ignores the second fitness objective. If you sum 2 or 3 or n fitness objectives, you'll very quickly come up against this problem. What's a potential solution? How might you try and correct evolution so that it doesn't lazily favor one objective?
You could add weights on them.
Let's add weights. Now, these two numbers are numbers that we're going to get back from the simulator. These two numbers are parameters or coefficients we're going to have to decide. So if evolution tends to favor optimizing this number rather than this number because this number tends to have a greater spread of magnitudes, then intuitively we want to make this number smaller and this number bigger. What? What should those two numbers be? Now I'm putting you on the spot, right? Hard to know. I don't know what these numbers should be. Very, very difficult to decide. This is another dirty little secret about machine learning and deep learning in general. Deep learning algorithms also tend to have fitness functions that look like this. They call them loss functions, more or less the same thing. How do you manually determine the weights to apply to these two desiderata, these two things that you want? Very, very tricky to get this right. It can take years of experience to learn how to do this. Becomes sort of artisanal machine learning. You have to do this very carefully. But the whole point of machine learning and robotics is to try and remove the human from the loop. We want to automate this process as much as possible. So simply summing two fitness objectives is not a great way to go. What else could we do? I just unintentionally gave you an alternative. Multiply them, right? So if any of these two numbers or n numbers in a product has a greater or narrower range of values, it doesn't matter now because we're multiplying them together. Yeah? What's the problem with this? Anyone tried multiplying 2 or 3 values together in a fitness function? Okay, you can try it. I'm sorry to break it to you, but evolution, natural and artificial, is usually smarter than us. She will find a way to set one of these values through mutation and reproduction and leave it at a relatively low number and push against another one. So it might be that it's easier for evolution to find a gradient, to start climbing the slope in the fitness landscape for one of these two numbers than the other one. So she'll find a relatively good value for one, and then through mutation and reproduction, keep increasing the other one. So put more simply, evolution will often find a way to still focus in on one value and not necessarily ignore the other one completely, but exert less selection pressure on it. It'll kind of ignore it. So we can't sum them together because then we need to manually determine weights. We can't just multiply them together because evolution will still find a way to pay more attention to one objective than another. So what else can we do? Tricky. Turns out that an alternative solution was formulated several decades ago, which is to do the following. This is known as MOO, an easy acronym to remember. This is multi-objective optimization. So in our case, the optimization approach is evolution, and we have multiple objectives we would like to optimize. In our case, the objective one is transferability. The other one is how far the robot moves from left to right. Yeah. This is, I'm going to do this example with just two objectives. So strictly speaking, this is BOO, or bi-objective optimization. What we're going to do is march down our set of evolved controllers. And let's assume that we're at the very beginning of this particular evolutionary algorithm. So we're starting with a population of random controllers, a population of sets of random weights. We take each controller and we evaluate it somehow. We send it to a physics engine, and that physics engine gives us back a number, how far the simulated robot traveled from left to right. And we assume that we also obtain a value for the second objective, which in this case is transferability. I'm delaying the explanation of how these authors actually calculate transferability, but let's just assume for the moment that transferability comes back, and this every controller can be evaluated for transferability, and let's assume that this metric ranges between 0 and 1. 0 means that controller is maximally non-transferable. Whatever the simulated robot did bears no resemblance at all to what the physical robot does when it's running that same controller. And a transferability value of 1 for a given controller indicates that that controller, when you run it on the simulated or real robot, there is absolutely no difference in the resulting behavior. So far, so good? Okay, so armed with this hypothetical transferability metric, we can assign 2 floating point numbers to every controller in the population. We can then represent the state of that initial population geometrically by interpreting those 2 objective values as coordinates in 2-dimensional space. Yeah, so let's assume in my initial population, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's assume I have a population of 12 random controllers. And this is the value, these are the objective values for each of those 12 controllers. Tell me about this controller up here. What is its position in this 2-dimensional space? Tell us about this particular controller.
It's really far away, but it doesn't transfer that well.
The simulated robot does a great job at moving from left to right, but completely fails to cross the reality gap. It's really good at objective 2 and really bad at objective 1. Tell me about this controller out here.
The opposite.
It's the opposite, right? This controller causes the simulated robot to not moving at all. It just stays still. Not surprisingly, if you take that controller and send it to a real robot, chances are that real robot also doesn't move at all. Really bad at objective 2, very transferable. Tell me about this one down here.
It's not very transferable, and it doesn't really do its behavior quite well.
It's kind of meh at behavior and terrible at transferability. Tell me about this one out here.
Good at transferability and behavior.
Okay. In this population of 12, we've now evaluated the 2 fitness objectives. Now we've got to kill off some of them and allow some to survive and reproduce. Which ones do you think get killed off?
The ones closer to the origin.
The ones closer to the origin. The lower and further to the left you are, the greater the chance of, yeah. Okay. What about this one and this one? Kill or keep? You could kind of make a case either way, right? They're kind of specialists. One is really good at one and terrible at the other. What about this one? Kill or keep? Is that a thumbs up? Keep? Okay. Yeah, it's not great, but it's certainly doing better somehow than these ones back here. But what does better or worse mean when we have two or multiple objectives? We're now in a multivariate situation. There's multiple variables, two variables we're dealing with. In the good old days where we only ever had one fitness objective, it was trivial to say who was better and who was worse. It was whoever had a higher value or lower value of this. But when you have multiple desiderata, how do you actually define better or worse?
I mean, can't you just use the distance function from origin?
We could, okay. We could use it, we could just say how far are you away from the origin. That's one way we could do things.
I mean, wouldn't it kind of depend on the transferability? Because, like, I don't know how, I mean, I know we don't know how it's calculated, but if, like, the one at the top that does the best behavior, like, it's not very transferable, but maybe even though it's not transferable, it still would do more than, like, the one in the middle, depending on how that metric actually functions.
Absolutely, it's a really good point. We haven't defined exactly how this transferability metric is computed yet, so it's a little hard to say. You're right. This one is doing really well, so even though it has low transferability, if we just look at the physical behavior produced by this one and the physical behavior produced by this one, they could be equivalent, or one could be better, one could be worse. Hard to say. Good point for now. You mentioned we could decide who lives and dies by how far away they are from the origin. So how far? How far do you have to be to survive?
Further than the one that's, further than the three that are closest.
3. Okay, I heard a number, 3. So we're back to defining a coefficient. We're going to have to come up with a number to determine something about who lives and who dies. Remember when we were adding two objectives together, we also had to come up with an additional number. In machine learning, this is often known as hyperparameters or hyperparameter selection. In machine learning terminology, parameters are the things that are being optimized. In our case, the synaptic weights. In machine learning, they usually don't talk about weights at all. They just refer to them as parameters. Parameters are things that are being optimized on their own. Hyperparameters are numbers that describe how the parameters get optimized. Choosing good hyperparameter values is kind of tricky, hard to do by hand. So it would be great if we could avoid as many hyperparameters as we can so that we don't have to manually determine them. So it turns out that in Mu, there is a way to determine who lives and who dies without having to rely on any hyperparameters at all. We as the implementers of Mu do not have to manually come up with a new number or a new threshold or a new weight.
So this is the Pareto fund, right? Where you just draw a box to any one point, and if it contains other points, you throw those contained points away. So you end up essentially just like drawing a squiggly line around the points that are the furthest away, without actually needing to define what that like furthest is.
Absolutely. So you mentioned the Pareto front, named after Pareto, an economist actually. So a little bit of economics this morning. Let's imagine you're in the market to buy a house. You go house hunting, you shop around, you go and visit a lot of houses, and some houses are bigger or smaller than others. All things being equal, you'd probably like a bigger rather than a smaller house. But surprise, surprise, generally speaking, the bigger the house, the more expensive it is. On your travels, you visit one house, which is smaller and more expensive than another house you visit, which is bigger and less expensive. Assuming that you're only interested in these two desiderata, of course, when you're house hunting, there's a lot of other ones, but for now, we'll just keep things simple. You're probably going to pass on the smaller, more expensive house because that house is worse on both desiderata compared to some other house that you've seen. You mentioned the Pareto front, which we'll get to in a moment. I'm going to introduce a little bit more terminology here. So in my house example, the smaller, more expensive house is dominated by another house you visited that's larger and less expensive. A dominated solution is one that is worse on all objectives compared to some other solution in the population. So let's play the Pareto game. Let's randomly pick a dot. Let's pick this dot here. Is this dot dominated or non-dominated? Non-dominated meaning there is no other solution in the population that is better than that solution on all desiderata. Dominated, non-dominated?
Non-dominated.
Non-dominated. So let's have a look at this controller up here. This controller is better at behavior, but worse at transferability. This one over here is better at transferability than this one, but worse at behavior. It's non-dominated. How about this controller chosen at random? Dominated, non-dominated? Dominated, right? It's dominated by this one and by this one, and I guess by that one as well. We can visit each individual solution in the population and label it with a binary label, dominated or non-dominated. After we've done that labeling, what do you think happens to the dominated solutions?
They get killed off.
You're gone, right? In the same way that you ignore that house in your house hunting exercise. Okay, so what you're left with at the end is a non-dominated front, or as you mentioned, the Pareto front. So all of the white dots here are dominated by some other solution in the population. They've been hollowed out to indicate that they've been killed off. And on the Pareto front, if you draw a line connecting all of these dots together, we have 1, 2, 3, 4, 5, 6 surviving non-dominated solutions in the population. When I made this slide years ago, I made a mistake, which I've left in to test your intuition about Pareto dominance. One of these dots is mislabeled. Which one? One of them that's labeled non-dominated is actually dominated, or one that's labeled as dominated is actually non-dominated. I made a mistake. Where is it? I should have numbered these so it'd be easier. Did you find it?
Is it the white one that's like under the, it's the white one that's like that one?
I see you pointing this way. This one?
Yeah, maybe. I don't know.
So I labeled this one as dominated, indicating that there is another point that's better at behavior and better at transferability than this spot, than this point. There isn't one, right? There's no point that is above and to the right of this point. Again, there's some nearby that are better at one of the desiderata, but worse at the other one. So the Pareto front should actually go one here. Yeah, everybody see that? Okay, all right. So why is it called a front? Well, there's a military metaphor here. As we start to run this evolutionary algorithm, we delete these individuals. There are 1, 2, 3, 4, 5, 6, 7 survivors. We roll a 7-sided die. We pick one of the 7 survivors at random. We allow it to produce a randomly modified copy of itself. And we keep rolling this 7-sided die until we eventually reproduce 1, 2, 3, 4, 5 new individuals, new offspring, to replace the 5 dominated solutions that we just killed off. And we now are back to a population of 12 controllers. We evaluate the behavior and transferability of those new 5 individuals, calculate who's dominated and who's not, delete those that are dominated, make randomly modified copies of the non-dominated survivors, and repeat this process. How does this picture change as evolution starts to roll on from one generation to the next? What's going to happen?
The front expands.
The front expands. Good point. Maybe. What do you mean by expand?
Like it moves like farther and farther away from the origin.
It moves further and further away from the origin. You hope that the non-dominated members of the population march further and further up and to the right. As they do, progress is going to get more and more difficult up and to the right. We're drawing on this military metaphor of an advancing front. Why does resistance increase? Why does it get harder and harder to push up and to the right? Where's the resistance coming from?
The like subset of like controllers that like meet in that or like that are beyond the front is just smaller.
It gets harder and harder, right? In essence, all of these points are still climbing slopes in a fitness landscape, and the higher you get, the fewer and fewer solutions that exist that will take you even higher. So typically you'll see the front move relatively quickly up and to the right, and then gradually slow down as you go. Yeah? Okay. Let's here's the math describing dominated and non-dominated solutions down here. Let's again exercise our intuition about mu. I'm showing you BOO, bi-objective optimization. How about, I don't even know how to pronounce this, uni-objective optimization. Assume we go back to just one objective, and we use this way of deciding who lives and dies. If we only have one objective, then all of the 12 points are always going to just be on the vertical axis. There is no horizontal axis anymore. In that population of random controllers, where we evaluate the behavior of all 12, how many non-dominated solutions are there among the 12? Just one, right? By definition, there's always going to be one that's at the top. Everyone else is dominated. All the other 11 solutions are killed off. That one individual is allowed to produce 12 offspring to replace itself, and off you go. In BOO, in bi-objective optimization, in this cartoon, there's about half the individuals are non-dominated. Let's go to 2, tri-objective optimization. Now you have to imagine a cube. Imagine a sprinkling of points inside that cube, a sprinkling of 12 points inside that cube. What does your intuition tell you about who's going to be dominated and who's going to be non-dominated in that 3-dimensional space? A little harder to think about. In this case, the fraction of dominated to non-dominated solutions is about 50-50 in 2 dimensions, or for 2 objectives. When we went to 1 objective, the fraction dropped to 1 and n-1. There were many fewer non-dominated solutions than there were dominated solutions. What happens in 3 dimensions?
There's like way more dominated solutions than non-dominated solutions.
Way more dominated solutions?
Yeah, because the volume of the behind the front.
The volume behind the front is greater, so maybe, what do folks think?
I think it's the opposite. There would be more non-dominated because now you have 3 parameters that you have to be the best at.
Exactly. The fraction, the number of non-dominated, the relative fraction of non-dominated solutions goes way up because becomes easier to be non-dominated, right? It's very hard for someone else in the population to be better than you at all three things. Yeah. What happens if we go to a tesseract? So four dimensions.
Same idea. You might even not see any dominated solutions as you get to too high of a dimension.
Absolutely. The moment you go to 4, can you find even one solution where there's some other solution in the population that's better than you at all 4 desiderata? House hunting is hard for a lot of reasons. This is the main reason. Typically, you're not just interested in size and price of the house. There's maybe 3, 4, 5, 6, 7, 8 other things you're interested in. And all the houses you visit, if you're a nerd and you put all the data into a spreadsheet, they're all going to be non-dominated. It becomes very hard to easily say, not that house, not that house, not that house, because they're dominated by some other house in your set. Very tricky. So multi-objective optimization, very popular, very widely used in machine learning, but it has to be used carefully because it works well if you have 2 objectives. When you go to even 3, you can get things like collapsing of the front, meaning that everybody's on the front. The evolutionary algorithm says, I can't run because the next thing I'm supposed to do is kill off the dominated solutions, and there aren't any. Therefore, there's no open slots in the population. Therefore, none of the parents can produce an offspring, and the evolutionary algorithm grinds to a halt. Okay. This lecture, strictly speaking, is about sim to real, but I wanted to spend some time talking about Mu because some of you have probably bumped up against this problem, which is you now have multiple things you would like your controller to get the robot to do, and you might be struggling with ways to combine these desiderata together. So if you're relatively comfortable with your programming abilities, I would highly recommend trying BOO, try bi-objective optimization in the way we just described. If there's 3 things you want your controller to do, and you have a really good laptop, you can create tri-objective optimization, but you're going to need a very, very big population, big enough to ensure that at any given moment there's at least some dominated solutions in your population. Yeah. We've been using bi-objective optimization in my research lab for almost 2 decades now. And no matter what the robot is, what the fitness function is, it turns out that whenever we run this, there's usually about 12 individuals that are non-dominated. I have absolutely no idea. I don't know what's special about 12. If anyone's interested in mathematical puzzles, I'm all ears. Okay, so here we go. Let's go back to our hypothetical transferability approach here. Let's assume that these individuals have all been killed off. This parent was chosen at random, and this parent produced by chance this child that obtained this transferability value and this behavior value. What happens next?
Now the one next to it is dominated.
Right? It's a tough world out there. So the offspring is now dominating its parent, which means the parent gets killed off, and the front has taken one small step up and to the right. Yeah? Okay, that was a hypothetical example. Let's come back to the transferability project. We're now looking at real data. I'm going to walk you through this. Real data. So on the vertical axis here, we have covered distance in simulation, measured in meters. We're dealing with some French nationals here. God bless the metric system. So we're measuring the distance traveled by the simulated robot in meters. Okay, and in brackets here to maximize. We're trying to make this value as high as possible. The horizontal axis here is reporting transferability, but it's reporting transferability in terms of approximated sim to real disparity. So as an observation was made a few minutes ago, the easiest way to measure transferability is to measure actual sim to real disparity. What's the disparity or the distance between simulated sensor values and real sensor values? As you're going to see in a few moments, these investigators are able to approximate or predict sim to real disparity before they go to real. I'll show you how they do that in a moment, but for now, trust me, they can do this. Because we're measuring transferability as a distance, we want to minimize that distance. The more transferable a controller is, the less disparity there is between sim and real. So far, so good? So we want to make this value as high as possible and this value as low as possible. So thankfully, they've provided a visual aid to us here, which is a reminder that evolution is trying to push up and to the left. So far, so good? Okay, we got a whole bunch of points here. Let's start with all the x's. These were x's at generation I. So this is partway through an evolutionary process. They've already been evolving the distance and the disparity of the controllers. And you can see most of the x's are sort of clustered down and to the right. Not quite what we want. A generation later, we have the circles. So the circles are the randomly modified offspring of a bunch of the x's, and things are getting better at this point. We've got some more fit children here. Black circles are the non-dominated solutions. So I want you to visually draw a line connecting all the black dots, and that line segment is the Pareto front, and behind that front, to the right and below the front, are the white circles. These are the dominated solutions. So this is sort of a snapshot showing optimization of actual controllers on actual robots that's gradually moving up and to the left. The evolutionary algorithm is obtaining controllers that increasingly move the simulated robot and increasingly are predicted to transfer well from simulation to reality. Next time, I will tell you how they compute this metric. A reminder, you have a quiz due tonight. You're working on milestone 3. I will see you all on Thursday. Thank you.